Hello, it's Mr. Rops here, and we're on example 4 here for diagonalization and transition matrices. I just have to warn you, like, this is a 4-part question, and it is going to be long. There are lots of components to this problem, and it will take me 15 to 20 minutes, I think, to make it through it. So bear with me, pause and speed ahead as you see fit. So we'll read it together. It says, Mr. Richards gets upset at work because he notices that some people leave the refrigerator door partially open. He estimates that the door is currently left open 10% of the time, and he suspects the problem is getting worse. Mr. Richards has noticed that the state in which a person leaves their fridge open depends upon how they found the door. Similar to the litter. If people see litter on the ground, they're more apt to litter as well. He thinks the same thing about the refrigerator door. He makes a table of his observations as shown, as this table here. And so we let S sub naught, sub 0, be this matrix, and T be this matrix, which is the transition matrix. Explain S sub 0, this particular matrix here. Well, S sub 0 is our initial state matrix. And in context, what it's saying is this. It's Mr. Richards' current believed state that their fridge is open 10% of the time and closed 90% of the time. So this is the initial state of being, is what Mr. Richards believes, and that's what S sub 0 represents. We'll get rid of that for now. Okay, so B part now says express T in the form of P, D, and P inverse. Well, P are the eigenvectors, and D is our diagonal, which comes from the eigenvalues, and this is the inverse of P. So we need to find the eigenvectors and eigenvalues of T. So in order to find the eigenvectors and eigenvalues of T, we have to solve the characteristic equation, and the characteristic equation, remember, is that the determinant of, well, in this case it's T, in the past we've called it A, minus lambda I equals 0. And so this matrix T minus lambda I is, I'm going to go 0.3 minus lambda, 0.2, oh, I just see a typo here, this should be 0.2 for 20%, and then 0.7 and a 0.8 minus lambda. Here is this matrix here, an absolute value of it means I'm going to find the determinant and I'm going to make it equal to 0. So solving the characteristic equation, I'm going to get 0.3 minus lambda times 0.8 minus lambda. Subtract the product of 0.7 times 0.2 equaling to 0. I have to solve this characteristic equation. I have my calculator for me, and doing this algebraically will be quite a mess. So I'm just going to grab it, but I'm going to graph it. If I use my calculator, the same premise, I just type it in, and I find my x-intercepts, and I get 0.1 and 1 as my eigenvalues. And so lambda 1 is 0.1, and the other lambda is 1. So these are my two eigenvalues, and so I now know that D is equal to 0.1, 0, 0, and 1. To find my P, I have to find the corresponding eigenvectors. So if I take the first one, which I'll do in green, I know if I plug 0.1 into my matrix T minus lambda I get 0.1 minus 1 will be 0.2, and 0.2, 0.7, and negative, or 0.8 minus 0.1 will also be 0.7. I know when I multiply that times xy, I have to get 0, 0. Well, this gives me the equation 0.2x plus 0.2y equaling to 0. They're both the same equation. I can multiply or divide through by 0.2, which gives me an x plus y is 0. And so x is equal to negative y. And if I let y be 1, if y is 1, x will be a -1. And so this is a nice straightforward eigenvector. And so now when I start to create what p is, p will be -1, 1 in this order because it corresponds to 0.1. Similarly, switching over to my purple color, if I want to find the eigenvector for lambda 1, well, when I plug that value into this matrix here, 0.3 minus 1, I get -0.1, 0.2, 0.7. And when I take 1 and plug it into here, 0.8 minus 1 is a -0.2. So -0.2. I see my nice symmetry here. And so times xy will give me 0, 0 again. And so I know that -0.7x plus 0.2y equals 0. Shifting it over, I know that 0.7x equals 0.2y, getting rid of the negatives. If I divide, if I multiply both sides by 10 and then divide, I can get x is equal to 2 over 7y. To find my eigenvector, if I let y be 7, so it cancels nicely. If y is 7, then x is 2. So here are some nice whole numbers to be one of the eigenvectors of the infinite that are possible, but this is a nice one. And so now I know part 2 of p is 2, 7. Not 2, 7, but 2 over 7. So that is my p vector. I then need to find my inverse as well. So the inverse switches these two values. So this is 7, and this is -1, and then it puts a negative sign on these. So it'll be -1 and -2. And I also have to do 1 over the determinant, which is -7, subtract 2, which is -1/9. And so that's a whole lot of negatives here. And so for ease of computation, I will just keep the 9 out, but I will distribute the negative so that there is one less negative. These are less negatives to deal with. I'm better with positive numbers. I make less careless mistakes. And so now I have P inverse, and D, and I was supposed to express T, P, D, P inverse. So I know that T is equal to P, which is -1, 2, 1, 7, times my D, so this is P, D, P inverse. D I know is 0.1, 0, 0, and 1. And making some space here, P inverse was -7, 2, 1, 1. And I'm going to put the 1/9 out front of here. And so now this is answering part B. There was a lot there to deal with. Okay, so now moving to the next part, here's the question again, reiterate. Now it says show that t to the power n equals this mess of a matrix. And so I have to take this mess of a matrix and I got to find t to the power n. Well, one of the things I also remember is this particular formula, which is given to me in the formula booklet. So if I want to find t to the power n, I can raise d to the power n, and that will be able to, and then do the computation from there. So let us continue here. Let us make this now. I want to put this to the power of n, which means d is to the power of n, which means this is to the power n, and I have to show with all my work that that is indeed what the matrix is going to look like. I notice there's a 1/9 in front, so I'm going to leave that 1/9, not dealing with it. I'm going to do all this multiplication. This 1/10 is the same as 0.1. So there's a couple things that already match up. So let us give it a try, multiplying all this out. And so going on to C part. I know t to the n is equal to 1/9. Well, -1217. When I put the n in, I get 0.1 to the n, 0 to the n, which is 0, 0 to the n is also, and then 1 to the power n, well, that's always going to be 1. And I have this here. And then I'm going to multiply these matrices together. So here's the 1/9. And go -1 times 0.1 to the power n plus 0. So this is going to be -1 times 0.1 to the n. -1 times 0, and then 2 times 1. And then 1 times 0, 0.1 to the n. 0, and then 7. -7, 2, 1, 1. And I highly recommend that you pause the video and try this multiplication yourself before you watch me do it, because then you can see if you're on the right track. So now I'm going to multiply this value times -7, which will give me a 7 times 0.1 to the power of n plus 2. So that's the first one. When I go to the next one, I'm going to take -1 times 0.1 to the power n times 2. So that's going to be -2 times 0.1 to the n. And then it's going to be plus 2 again. And going to the bottom row, it's going to be 0.1 to the n times -7. So that's -7, 0.1 to the n plus 7. And finally, 0.1 to the n times 2. So 2 times this plus 7. And hopefully that is the same as what they were asking for. A little bit tricky, the computations there. But when I look at it, this is indeed, these are equivalent to what is written here. Excellent. Next part then, D says, hence, determine the steady state of the refrigerator door and comment if Mr. Richards' concerns are justified. Well, if I want to find the steady state, S, that means I can take t to the power n times S0, and I want n to go to infinity. Well, that means I'm going to take this matrix that's up here to here, and I'm going to take that and multiply it by Mr. Richards' claim of 0.1, 0.9, which we were told in the initial question was S sub 0. When we take n and go to infinity, 0.1 to the power of n, well, that's 1/10 times 1/10 times 1/10 times 1/10. That goes to 0. So this cancels away, and I get 2. Same thing here, 0.1 to a great big giant power. That's going to be 0. If you're not sure, throw it in your calculator and see. This is 2. Similarly, this will be 0, and so this is 7. And this will also be 7. If I multiply that by 0.1 times 0.9, well, when I do that, I got the 1/9 still. And I get 0.1 times 2, and 2 times 0.9. That multiplies, so that's 0.2, that's 1.8. That multiplies to 2. 7 times 0.1, 7 times, so that's 6.3, 0.7. This is also 7. And so then I get 2/9, and 7/9 is the steady state vector, which is approximately 22.2% and 77.7%. And so is Mr. Richards' claim justified? He should be worried. The refrigerator door is open, the fridge is open over the long haul 22% of the time. So Mr. Richards should be concerned. is truly concerned and justified. All right, so there is a lot there. It uses much of our matrices information with steady state matrices, diagonalization. We found out with explained S naught. We found our eigenvectors and eigenvalues. We used them to find to the power n and actually compute to the power n. And we use that value to calculate if Mr. Richards was concerned if they were justified.